It's much more interesting to look at your faces than to stare at black squares. Yes, Enrique. Yes, Jeffrey, Brian, Drumarl, Moshe, would be nice to see you. Safa. Oh, thank you guys. Brian, Jeffrey, who else is here? Tre, Elmira. All right, so let's start. So I hope, guys, you remember what we talked about last time. And that was about the trig functions. About the trig functions. So we know that the angle is measured in radians, and that's the length of the crust, right? We measure the length of the crust and how many radius units that fits. If we measure the x and y in radius units, then the green segment is cosine, the red segment is sine. And I hope you remember from last lecture how to find the remaining sides, how to see tangent, how to see cotangent, how to see secant. Do you all remember how you see secant, guys, for instance? Secant is, where do I look at secant? Just quick verification. If I really want to see secant, what do I look at? Very good, hypotenuse. Couldn't have said it better. Hypotenuse. You understand, guys? Secant is 1 over cosine. 1 over cosine means that I would prefer to divide not by cosine since it's less than 1. I would prefer to divide by 1. And to divide by 1, I just rescale the triangle. You can imagine dragging this longer. Actually, here it is, guys. The secant is in the picture. You see where secant is? It is right over here. You agree? That's my secant. You see why? Because I dragged this green side to be of length 1. That will drag the red side to be the same as tangent. Here it is. And secant will be this over this full length, which is the same as this over that. Then we verified that sine and cosine have this property, right? Sine is an odd function and cosine is an even function. Easy to see, yes? Just simply open to an angle theta, open to an angle minus theta. Sine is one segment, sine of the negative angle is the opposite segment across the x-axis, a reflection of it. And cosine remains to be the same x-axis segment. Does anybody see what do I rotate by to make minus cosine of theta? That's an interesting verification here, if you understand the concept. Okay, and so here, guys, is my unit circle. Here is my unit circle. And let's say that this is the tangent. So this is the sine and this is the cosine. So this is cosine theta. This thing here is sine theta. And the angle, let's say the angle is this angle theta over here. Actually, the angle theta is naturally here, right? I wrote it over here, but really this is the angle theta in radians. Good. My question is, how do I make it equal to, what change do I make to the angle theta? Same change, right? So we have here something, I hope you understand without me giving extra hints. I want it to be equal to minus cosine of theta. Something of theta, I want you to find the symmetry with respect to which you will get minus cosine theta. You can see that, for instance, sine of minus theta produce minus sine of theta. And cosine of minus theta does not. It keeps it as cosine of theta. What do I do to the angle to create minus cosine theta, please? You see this angle? Can you imagine what to do to create minus cosine theta? A transformation that works for every single theta. Not just the one I drew, but every single theta transformation that will do that. You understand my question, guys? It's slightly vague because to make it not vague, of course, I will have to reveal the solution. So the angle theta, I want you to create an identity that will produce minus cosine of theta. It doesn't have to be in the first quadrant. It's accidental that it's in the first quadrant. I hope you understand. This is just an illustration, like crutches to help you figure the formula. You have to think in the abstract. And the illustration is only crutches to help you see that. Look at it. Right? I'm giving you a huge hint. Right? If this is theta, then what do you want to do? Yes, reflection over y, precisely. Jeffrey, you nailed it. Reflection over y. How do I indicate reflection over y or rotation, or that would generate reflection over y? By changing the angle, please. Oh wow, it's so many answers. Rotate by 180 degrees. That's a possibility, right? So always the same angle and rotate by 180 degrees and you get negative. Just split. Very good idea, for instance, right? So instead of what I can do, imagine is if I rotate this by another 180 degrees, wherever I'm located, I rotate extra by pi, that will bring me here, and that will create the right reflection. Always. So brilliant, Jasprit, congratulations. That's one way to do that. Right, so for instance, I can say cosine of pi plus theta or theta plus pi will create minus cosine theta. You see, because add another pi and you are rotating from this angle again to make it a line, and that will be reflecting. Yes, it will make it minus. Do you see that? Just play the animation in your head. Whatever is the angle theta, rotate. Well, you are right. I better not do this, and my apologies. You see, here you go. I was conned into saying something wrong. Not quite, right? Because not quite, right? This is a nice idea for this particular quadrant, but it will not always work. Why will it not always work? Because the No, I'm sorry, it would always work. It would always work. Good. No, it would always work. So it's pi plus theta. And we will, sorry, of course it would always work. All I do is just, without thinking about the identities, you just imagine moving this line up and down, right? So that would always reflect it to the other quadrants. You know, if you're in quadrant 1 or 2, you will produce the reflection in quadrants, in 1 or 4. You would produce reflection into quadrants 3 or 2, and vice versa. Good. So that's very good, Jasprit. So next, we figured out how to convert position into position xy into the corresponding trig in terms of trigonometry, right? So if I know that this arc is theta and the length, let's say, is 10 centimeters, then the position on the x-axis is 10 times cosine, 10 times sine. Just to be sure, let me just recite that. Okay. Good. So here is some circle. And let's say that we know that the radius is measuring 10 centimeters. Yes, radius is 10 centimeters. And I want to find formula for the points x, y in terms of the angle, in terms of the angle theta, which is here. Yes, and I want to know what is x and y. Now, do you see that this thing here is sine theta, whereas this thing here is cosine theta? Right? Now, what's the relationship between those values and x and y? I would have said that cosine theta is identical, it measures the same thing as x. And sine of theta measures the same thing as y. I say measure the same thing because it's not using the same units. What is sine of theta measuring? It's measuring the vertical altitude in unit radius lengths. You understand? So for example, if I say cosine is equal to 1/2, 1/2 of what? 1/2 of the radius, right? If I say cosine is equal to 0.75 or something, then I'm saying that cosine is equal to 75% of the radius. So the length is communicated in terms of radius. Good. But if I measure in centimeters, that's not quite adequate, right? In centimeters, the red line segment is not sine. Right, so that's why I use triple bars. Here, the actual formula will be what? Would be that y equal to 10 sine theta and x equal to 10 cosine theta. Which, by the way, some of you, I imagine, might find my explanation very confusing, right? So you think, isn't it simple? I mean, just sine is opposite over hypotenuse, right? So most people in high school or wherever you're told to think this way. You can say, opposite over hypotenuse is equal to sine, and so y is equal to 10 sine of theta. That's absolutely adequate. The only thing that I want to emphasize, guys, is that what I'm trying to explain to you is what's the purpose of defining sine this way? What's the purpose of it, right? You're defining it in proportion to the radius. You understand? That's why you change those. Why is sine opposite over hypotenuse? Is because by doing so, you report your findings in terms of radius lengths by proportion to the radius. Understood? Guys, so confirm that you understand. I mean, this is a sort of review, but hopefully, it doesn't go over your heads. Otherwise, I'm wasting my breath. Yes, right? Understood? Beautiful. That's very important. We're going to use this identity in one moment. Predictably, today in both morning and evening class, we have fewer people. I guess people want to start early vacations. As they say, Aviv הגיע פסח בא, נכון? Elazar? You don't know. Then Avraham, you know, right? That's what they say? You don't know the song Simcha Rabba, Aviv הגיע פסח בא? From what planet do you come, Elazar? But you know Avraham, right? You speak Hebrew natively or not?
I speak Hebrew. My wife's actually from Israel. But like, who sings that song though?
I don't know anybody. There are many singers. Just select which one. I mean, don't you know this? It's weird. I thought it's the most famous one for Pesach. So, where are we? So we all understand how I got r cosine, r sine, yes? Then what else do we have? We have Pythagorean Theorem. We have that cosine squared plus sine squared is 1. You understand why that's 1? Because cosine squared is the square of the adjacent leg of a right triangle plus the square of the vertical leg of the right triangle gives you the square of the hypotenuse. So this you know how to prove, correct, guys? We spent some time explaining the Pythagorean theorem, and that was a very trivial proof. You just take a right triangle, create a square out of that right triangle by rotating it appropriately, and you have the inner square is c squared, and the outer square is a plus b squared. Take the outer square, remove the areas of triangles, you have the Pythagorean theorem. Could not be simpler. So now, guys, let's remind ourselves of the angles that we had to deal with. Right, you know, in high school, you took trigonometry in high school or in college before this class, obviously, right? So you took either in high school or in this class, you've taken some lectures in trigonometry. Yes. And so the angles that they always talk about is pi over 4, pi over 3, and pi over 6. Why those angles? Well, let's look at it, guys. Pi over 4 is easily produced by taking a square and cutting it through the diagonal in half. If the square is of sides 1 and 1, the angle used to be pi over 4. Now it's pi over 2, I'm sorry. Cut in half, it's pi over 4. And what do we have? Pi over 4, guys, by the way, pi over 4 is the angle of your American pizza slice. You know that, right? Because you cut the pizza into 4 and then each piece you cut again into 2. So the ideal pizza slice is at 45 degrees in America. So pi over 4, and the hypotenuse is square root of 2. Good. So then I can easily read trigonometric identities. Like, for instance, what's cosine of pi over 4? It's simply adjacent over hypotenuse. It's 1 over root 2, which is root 2 over 2. I just multiply numerator and denominator by root 2 to normalize the denominator. Good. Now, please help me with the following calculation, guys. Please calculate what is tangent, secant, cosecant, cotangent of pi over 4. Very rapidly, tell me, please, what is tangent of pi over 4 and what is secant of pi over 4. And I'll be convinced you know the rest. "30 students, 30 responses," yes? So far I see 2. Okay, so what is tangent? Jeffrey, you say tangent is root 2 over 2. No. Safa says the tangent is 1 over square root of 2. No. Yes, guys. So what you do is write tangent of pi over 4 equals secant of pi over 4 equal, to be sure, right? So, I mean, of course, if you say Alexander, I see what you said. So it's perfect. But in general, so that I know what you refer to. So tangent, you're saying it's 1 over root 2. No, Sophia. Cosecant, it's root 2, yes. Tangent is 1. Guys, it should not take you any time, guys. I mean, the picture is right in front of your eyes. It should be like as long as it takes to type. And you're much faster typers than I am. Yes, well, we don't mess up SOHCAHTOA because we do not, I will mention in my comments below, we forget about this nonsense, right? In this class, there is no SOHCAHTOA. In this class, there is brain, right? Because if you don't have brain, I mean, SOHCAHTOA is not going to help you, I'm telling you, right? All right. Cosine is not root of 2. Well, that's Elazar. Yes, that's actually true, right? God helps you. I mean, I see very few answers that look to me nice. So first of all, tangent. What is tangent? Tangent of pi over 4, it is opposite over adjacent, right? Which is 1 over 1, which is 1. Good? You can see it in the picture. What is secant of pi over 4? Secant of pi over 4, look at it, guys. This is hypotenuse over adjacent, root 2. Good? What is cosecant of pi over 4? Cosecant of pi over 4, it's hypotenuse over opposite. Happens to also be root 2. Good? Now, if you understood this, guys, please tell me what are the values of, let's say, cosine and sine at 3 pi over 4. You understand? 3 pi over 4. I want to, so how do we use that, the fact that we know what is cosine and sine at pi over 4 to figure out what it is for 3 pi over 4? The question is for 3 pi over 4, what is sine and cosine? Okay, Safa. Well, I'm not sure what you mean square root. I see, accidentally typed square root of 2 over 2. Square root of 2 over 2. And cosine. So guys, if it's not automatic for you, obviously over spring break, that's what you're gonna try to train, yes? This thing has to be automatic. And what we're doing, and that's why the exam is not yet given, is that I'm trying to adjust you to what you are supposed to know before this class begins. Those are prerequisites. You're supposed to come knowing trigonometry perfectly, like I don't even have to mention it. But that's utopia, that's not true. All right, so let's draw a picture. So what is 3 pi over 4? Let's think about what is 3 pi over 4. It means that I go, here is 1 pi over 4, 2 pi over 4, 3 pi over 4. I'm in the second quadrant. You see, I move 1/2 and another quarter of a half. Sorry, another half of a half, another, right? So I move to 0.3. And here is my sine. And here is my cosine. Do you see that? What do we see about the sine? Cosine is negative and sine is positive. But aside from that, what's the angle here? The angle here is the same as what I have over here, right? Same situation as what I have over here. You agree? Just over here it's plus. So it's really like 45 degrees, or it's like pi over 4, but in second quadrant. So then I see that cosine of pi over 4 is minus root 2 over 2. Sine, on the other hand, of pi over 4 is root 2 over 2. What is tangent? Oh, sorry, this is 3 here. What is tangent of 3 pi over 4? Minus 1, very good. The answer is minus 1. Good. Now, if I wanted to calculate what would be this angle if it's if I want to get to 45 degrees in the third quadrant, what's this angle? So this is 3, then this is 4, and then this is moving 5 segments. You agree? You see how I think, guys. 1, 2, 3, 4, 5. So this angle is 5 pi over 4. And I can easily calculate all my values there. What about this position? It would be what? If I want to get to here, this is what angle? If I move counterclockwise? 7 pi over 4, because you see, you move 7 pieces. Altogether, it's 8 pieces. You move through 7 pi over 4 slices, you see? So this here is 7 pi over 4. Easy, right? So no arithmetic, it's very obvious where this is located. Just think about it, right? Or you can think of 7 is not divisible by 4. 8 is divisible by 4. 8 over 4, it's full slice, and then subtract 1 slice backwards, okay? I'm sure you are much better at it than me. Good. Now, what about other angles? Another angle can be easily obtained if I take equilateral triangle. This picture is not quite good. It's not exactly equilateral, but in an equilateral triangle, guys, it means that all the sides are 1. So this side is 1, this side is 1, and this side is also 1. Now, if the sides are all the same, the angles are all the same. Do you see that? The inner angles, each inner angle is like any other inner angle of an equilateral right triangle. You can see it kind of like this. You see it, guys? Here is a better illustration of an equilateral triangle. You can see that all the angles are the same. You can rotate the triangle into itself. You can imagine one triangle rotating into itself, or any other way you like to observe that the angles are the same. And we already know that the sum of the inner angles is pi. So if each of them are the same, then each has to be pi over 3. Do you agree? Same piece plus same piece plus same piece equal to pi. Each of them is pi over 3. Do you see that? So this angle is pi over 3. Now I cut the triangle in half. So what is this? This is pi over 6, because I cut it everything in half, 90 degrees, right? Or pi over 2 radians. They cut it in half. Now this side is now 1/2. And now what do I obtain? I obtain right triangle of angles pi over 3, pi over 6, 1/2, 1, and the remaining side, it's square root of hypotenuse squared minus side squared, which is root 3 over 2. Are you with me? Do you see how I obtain root 3 over 2? Now, you understand, guys, even a while ago, this is something that if you bother to think about, you could easily come up on your own. You understand? Just if you think about it, why those angles are used to, you could have come up with this formula on your own, I'm sure of it. Now I can read a lot of other immediate values. So tell me, for instance, what is cosine of pi over 3? Cosine pi over 3 is what? From the picture, cosine of pi over 3 is what? Very good. Now, 1/2 of what, please? Cosine of pi over 3 is 1/2. 1/2 what? No, 1/2 is not 1/2 pi. 1/2 of what? When I say cosine of pi over 3 is 1/2. Oh, here you go. Radian, exactly. We'll take a small break afterwards. So, you know, I have actually a song that goes in my mind when I think of trigonometry. You might know it. Do you know the song? Oh, the radian. I cannot sing too well, but do you know the song? If not, I'll show it to you, don't worry. Or maybe a small part of it. On the radius, to be more precise. No? Good. Today somebody in the morning asked me to sing, so I played them that song. All right, good. So we understand what is cosine of pi over 3. It's simply, what is the 1/2? This is the radius, you understand? That's why, I mean, it's adjacent over hypotenuse, and if it happens to be just the size of the adjacent, it means we're measuring in radius units. The hypotenuse is the radius there, right? That's what radian measure is about. It unifies the length of the angle with any other measurement. They're all kind of you are measuring all of them using the same scale. Good. So what about sine of pi over 6? What is sine of pi over 6? You can see it in the picture. Yes. Exactly. So you can just see opposite is 1/2 over hypotenuse. Good. And may I trust that you know what is cosine of pi over 6? Cosine of pi over 6 is what? Root 3 over 2. Exactly, right? So you just cosine of pi over 6, it's adjacent, which you calculate as root 3 over 2. Good. All clear? And may I trust that you will know how to do the calculations of all functions. For example, guys, what is sine of 2 pi over 3? Could you tell me what is sine of 2 pi over 3, please? Sine of 2 pi over 3, without any SOHCAHTOA or any nonsense like that. Just think about it. What is the value? Okay, we have a few people. Exactly, right? What is 2 pi over 3? It means that I tend to think this way. It's the same as moving to pi. If it's 3 pi over 3, it's pi, right? And then moving back a pi over 3. So it's pi over 3 in the second quadrant, which means sine is still positive and cosine is negative, right? And what is sine of pi over 3? Sine of pi over 3 is root 3 over 2. You understand how we get it, guys? So instead of memorizing SOHCAHTOA, I just try to figure out, well, you can take this triangle, cut it in half, you get those angles. Good? You see why those values are so naturally simple. Good? And so I will leave it to you to verify the remaining trig functions. You see, you're supposed to, so I have those procedures for 5 pi over 6 and for everything else. If you have this triangle in your mind, you can easily, in 2 seconds, draw it, and in 2 seconds, figure out the ratios that you have, right? So for example, very briefly, what is tangent of pi over 6, please? What is tangent of pi over 6? From this picture. Wonderful, Alessandra. 1 over root 3. Very simply, just look at the tangent of pi over 6. You just look at this angle. Opposite is this, adjacent is this. So what you have is 1/2 divided by root 3 over 2. And multiplying both things by 2 gives you 1 over root 3. You can also write it as root 3 over 3 if you prefer, right? This is the same as root 3 over 3. Very good. Now we come to a very important part of this class, guys. How do I figure out, let's say, something like this? So let's say I want to calculate cosine of pi over 3 plus pi over 6. Yes, I want to make this calculation. And now watch me carefully how I'm going to do that. Okay, so we have cosine multiplied by pi over 3 plus pi over 6, which means, of course, I distribute the cosine right through the parentheses, like this, and like this, getting cosine of pi over 3 plus cosine of pi over 6. And what is cosine of pi over 3? Well, cosine of pi over 3 is 1/2. And what is cosine of pi over 6? It's root 3 over 2. And my answer is simply 1 plus root 3 over 2. So did you write it all down? Yes? If you wrote it all down, please confirm now that you understood. Lazar, you didn't have time? Okay, you can write it down still. And now, please write, I have 28 names here, I think. I think 28, where is, yes, it is. So, and then write that, yes, I understood what you understood what I did. You see, cosine multiplies by pi over 3 plus pi over 6, distribute through the parentheses, and we solve it. Please confirm that. I want to see 27 confirmations. I think one of those 28 people is me. 9, 10, 11, 12, 13, 15, 17. Okay, I'll release the cat and you continue writing. I'll check once I have all of your signatures there that you're following. $19, well, it's getting there, but it's not 27 or 22, 20, what? Come on, faster. Get in line, faster. All right, let's see what we write. Okay. Can distribute. He gonna bait us. You probably can't do this. Yes, yes, yes. Yes, sir, but enough of you said yes, yes, yes. Kitty, yes. I let the kitty go. What is that, Elazar, in Hebrew? What is it? Mas? You want me to charge taxes or something? Yes, it's true. Foolishness requires charging taxes, because what I just told you is absolutely and terribly, disgustingly, stupidly wrong. So when you do that, it means you haven't thought about this problem at all. And I mean, maybe it's because you did not care about this problem. It's not important to you at the moment, right? But usually that's what people do. They take shortcuts, they listen to authority, like to me. And what happens when they listen to authority? Let me give you a hint, right? And maybe 7 of those. That's what happens. Because, well, let me show you. So if you think about it for a moment, guys, what is that? This is cosine digesting. This is not multiplication. Cosine has eaten pi over 3 plus pi over 6. It has eaten an angle. It's digesting it, guys. How long ago have you been eating food? When you digest something, do you multiply it? It's a if I, what's happening, for example? That would be a very, very interesting universe indeed if, for instance, here you are. I'm going to give you some nice belly here. And here, let's say what you did is you ate 2 ice cream cones, right? So according to your logic, if you can distribute it, what's the result? The result is that you would have you with 1 ice cream cone and another copy of you with another ice cream cone. That would be a very interesting universe indeed if that's how you were digesting your food. Yes, that's what you just said, you know, when you distributed cosine and sine, and when you confirmed that what I did was right. Digestion is usually very complicated. It's not what's happening. You follow? Now we're going to try to understand what is the situation, guys. So you can easily see that this distribution will not work, for instance, by selecting 0, selecting simple values. So 1 is equal to cosine of 0 minus 0. Yes? You agree? Because it is cosine of 0, it's 1. But cosine of 0 minus cosine of 0 is 1 minus 1, which is 0. Good? So we are going to try to establish the sum of 2 angles, difference of 2 angles formula for sine and cosine. Nicole, you disappeared. Why did you disappear? So don't disappear, guys. Okay, so here is some coordinate system. Sorry, I could have done it better, but here we go. So that's okay. Elazar, who lost all her weight? You mean my drawing, right? So here is the situation. I see. That's good. So here is the situation, guys. We want to understand what is cosine of beta minus alpha. We will understand the difference of 2 angles first. That will require some amount of effort. Ready? So I have the angle alpha and beta, and here is the idea that I will use. It's not an easy idea. So I select this to be of size 1, and somewhere else here is the other segment of size 1. And here I'm going to draw. I'm going to draw the angle alpha. This is the angle alpha, and this is the angle beta. Now help me please and tell me what is the coordinate here in terms of alpha and beta. You see the coordinate I underlined? What's the coordinate here, please? Elazar, not to remember, if you understand it, how can you, it's not memory, it's coming naturally out of you, right? Like vodka after a binge drinking. Good? Cosine alpha, sine alpha. You see, I mean, what's there to remember, guys? It's natural. When it's natural, then it's cosine alpha, sine alpha. Yes? Everybody understand? That's why we spend this time describing this point, right? Now, if you do, tell me this point is then what? The second point is, what's the coordinate of that second point? Exactly, cosine beta, sine beta. Everybody sees it? Grant, you see it? That's good. So cosine beta, sine beta, cosine alpha, sine alpha, and then guys, we can draw this segment C. Yes. Now we can use the distance formula to understand what you see. Do you remember the distance formula, guys? You know that you can measure the length of a line. Let me just remind you. If you have some coordinate system and you have a line with position A, B, and the other point is C, D, then I can complete it and make it the hypotenuse of a triangle. Here it is. Yes. So because it's a right triangle, I know that the red length squared plus the green length squared will be the hypotenuse squared. So if this is the hypotenuse, then the hypotenuse squared equals to what? It's equal to C minus A squared plus D minus B squared. Yes, that's how we have the length of a line segment formula. It just follows from Pythagorean theorem. So that allows us to figure out a formula for C squared. Are you ready? So the C squared is just the difference of the X coordinate squared plus the difference of the Y coordinate squared. Yes. So we get that it is cosine beta minus cosine alpha squared plus sine beta minus sine alpha squared. Yes, root of that is the distance formula. That's what we're using. We just have those 2 points and we're using the distance formula. Absolutely. Good. So what do we have when we simplify it, guys? Expanding the first quadratic, we get cosine squared beta minus 2 cosine beta cosine alpha plus cosine squared alpha plus sine squared beta minus 2 sine beta sine alpha plus sine squared alpha. Good. And now we can simplify that formula, guys. You see how we simplify it? We have this identity, cosine squared plus sine squared of the same angle, they reduce to 1. And this part, cosine squared alpha plus sine squared alpha, also reduced to 1. And we have the following situation here. We see that c squared is equal, this is red is 1 plus green is 1, so we have 2. And the rest is, we can factor out minus 2, so it's minus 2 cosine beta cosine alpha plus sine beta sine alpha. This is the formula we obtained for c squared. Observe, guys, that the angle in between beta and alpha, this green angle that I'm going to draw, this green angle, what is the length of that green angle? It's simply beta minus alpha. You see that? It's just beta minus alpha. Now I'm going to topple this triangle and I'm going to make this leg fall on the x-axis. The bottom portions of, well, the bottom portion, let's see if I can I cut here? The bottom portion is written, you don't focus on writing it because you have it written over here. You have this thing entirely written over here in the notes, right? So you guys don't focus on writing so much as you should focus on trying to understand. It's all in the notes. Good, this is what I do, okay? Cosine beta minus cosine alpha squared, blah, blah, blah. I just simplify it, I get this line. Good. You see this, guys, what you should remember is not the particulars, the calculation you should carry out. What do you remember? You remember the minimal amount of information necessary for you to recall such a proof. What's the idea of the proof? Why was it working? If you understand it enough, you probably remember it. Now you see I'm going to drop this segment. This is what I'm going to do, guys. I'm going to make you a small picture here and then we'll do another one. So all right, so what I'm doing is, you see this line? I'm dropping it down and now it's here. And the other line is somewhere here. I don't know where it is, right? So this is this line and this is this line. You can see that because it's rigid motion, the C is now connecting this corner to that corner. It's still the same length C. Yes, that's still C. Now, please tell me, what is this angle? Alexandra, you mean, yes, Jasprit, it's beta minus alpha, right? You can see that beta is this wider angle here. Yes, it's beta minus alpha, and then help me figure out what are the coordinates here and here. What are the coordinates here? I mean, I should probably do it in different color. What is this coordinate here? This point has what coordinates? Very good, it's 1, 0. What are the coordinates of this point? Very good. The coordinates of that point. Very good, Alexandra. So it's cosine beta minus alpha, sine beta minus alpha. Similar, just a different angle, you see? And so this is, now, I mean, I'm going to actually go back to my notes. Here it is. Here, guys, you see it? Cosine beta minus alpha, sine beta minus alpha. This is that picture without the circle. Good. I just take this triangle and I flip it. And so I have another calculation of c squared. It's just I use the distance formula for those 2 points. It's still going to get me c squared. You see? So c squared from the first picture is 2 minus 2 cosine beta cosine alpha plus sine beta sine alpha. You know how you would know that you understood this proof, guys? Like when I stop lecturing, when it's the lecture is over, can you prove it without looking anywhere on a piece of paper? Can you see the argument? If yes, then that means you understood. So what do we have here? We have c squared. It's cosine beta minus alpha, sine beta minus alpha minus 1, 0. And when I apply the distance formula, what do we see? We see this squared plus this squared. Expanding the first square, it's cosine squared beta minus alpha minus 2 cosine beta minus alpha plus 1 plus sine squared beta minus alpha. And I can simplify this plus that equals to 1. So we have 1 plus 1, it's 2 minus 2 cosine beta minus alpha. Look at the formulas, guys, please. You see, you see this? Do you see this part and do you see this part? They must be the same because this is equal to this. You see, this equality is equal to this equality. And everything is the same. You can just algebraically or just obviously see that this part must be the same as this part. It's 2 minus 2 times something equals to 2 minus 2 times something. But those somethings are the same. Good. So I now have a formula for cosine of beta minus alpha. This is the formula that we just obtained, guys. I hope you understood it. It's cosine beta minus alpha equal to cosine beta cosine alpha plus sine beta sine alpha. Very important formula, which will be important in our derivations very soon. Next, I'm immediately applying this formula to figure out cosine of pi over 2 minus theta. You see, it's a difference of pi over 2 and theta. For any theta, it's cosine applied to first angle times cosine applied to second angle, plus sine applied to first angle, and sine applied to second angle. Cosine of pi over 2, however, is 0, so this part disappears. Yes, this part disappears, and sine of pi over 2 is 1. So we know that cosine of pi over 2 minus theta is equal to sine of theta. Yes, this is just what we verified with, guys. We have this formula. We have cosine of beta minus alpha. We verified that it equals to cosine of the first angle times cosine of the second angle plus, the minus is a plus, right? Plus, we now have sine of the first angle times sine of the second angle. Multiply sines, yes, exactly, Lazar. So you multiply cosines, you multiply sines. It's easiest to remember this formula. Just change the sign, change the minus to a plus. By the way, as we're at it, guys, could you very quickly prove this? Tell me what is the identity. If this is beta minus alpha, please tell me immediately what and justify, okay? I mean, maybe you can feel the pattern, but I want you to justify what is cosine of beta plus alpha, the sum of the angles. What is the formula? And why is that the formula? Should follow immediately from this. Yes, but why? That's right, Elazar. And then, of course, explain very simply why that's the case. Safa, correct. Jomel, I'm assuming you just simplified BA as cosine applied to each of them individually. Addition and subtraction is the same procedure. In particular, I can always, this is the thing that you do, guys. I look at this expression, it means an angle minus another angle. And they are completely arbitrary angles. Yes, so what can I do here? I can simply write it as cosine of beta minus alpha. Do you agree? Because I know the formula when the main operation is minus. And that will give me cosine of beta, cosine of minus alpha, plus sine beta, sine of minus alpha. You agree? And then what do I know? Cosine of minus alpha is equal to cosine alpha, because we know the cosine function is even. Yes, and sine of negative alpha will be minus sine alpha because sine is odd. You see? So it takes just very few manipulations and you right away see that formula. The main work was in establishing the cosine of difference of angles. If you have that, the remaining formulas are very easy. Now help me, guys, to understand, right? So we know using this first theorem, we see that cosine of pi over 2 minus an angle theta, that is cosine of pi over 2 cosine theta plus sine of pi over 2 sine theta. And this is simply cosine of pi over 2 is 0, so this is, and sine of pi over 2 is 1, so this is simply sine of theta. Agreed? And I proved that for all angles theta. Now please tell me, how does this, what does it imply, and how does this formula now allow us to figure out what is sine of pi over 2 minus theta? So I want to understand how to simplify sine of pi over 2 minus theta. What do I do? Give me the answer and give the answer in terms of cosine of this formula. It should be following from this formula. But we don't, Sophia, you see, how do you get that formula? Sine, sine, cosine, cosine. Maybe that formula is not right. You see, you need to always move from something that you know to something else that you know. You don't need to do a lot of work here, guys. Look at it. What is the, you have to read what this is saying. This is saying cosine of pi over 2 minus an angle is equal to sine of that angle. So look what I'm going to do. Do you agree that this is an angle? And I can quickly convert it to cosine. It's not cosine of 0. How can it be? It's not, it's theta, right? It's not just cosine of 0 is 1 then. So if this is an angle, then I can write that this is cosine of pi over 2 minus the angle. Do you understand? What is this saying? You're focusing perhaps on the theta, and that's why the problem looks like it's different. What this is saying is cosine of pi over 2 minus any angle is equal to sine of that angle. So sine of that angle is equal to cosine of pi over 2 minus the angle. Are you with me? Do you understand what I'm saying? Yes, guys, the theta is not what is not important to the statement. The statement is pi over 2 minus an angle. If you apply cosine, you will get sine of that angle. So sine of that angle is pi over 2 minus the angle times cosine. No, not times, they apply cosine applied, right? So like this. Good. And then I can simplify it. Look at it. So here I can just use basic algebra. Pi over 2 minus pi over 2 is 0. Minus times minus is plus. So the result is simply, it's simply cosine of theta. Do you see it? I did not expand. I mean, it was just logically an immediate consequence. Yes? In case you would like a geometric crutch, look what's happening here. You see, we have verified that cosine of pi over 2 minus theta is sine of theta, and that sine of pi over 2 minus theta is cosine theta. Now, if I look at this picture, it's pretty obvious that that would be the case. Do you see this picture? If I draw an angle of theta, and I just decided to draw it in the first quadrant, I mean, you can try drawing it in other quadrants. If theta is in the first quadrant, this is the picture. So this is theta. This angle is pi over 2 minus theta. Yes, pi over 2 minus theta is this angle. So what do I have? I have that this is sine and this is cosine. Now, what is sine of pi over 2 minus theta? It's this line. Sine of pi over 2 minus theta, you can draw this thing. And it's the same as cosine. And what is cosine of this angle? It's the same as sine. This picture explains it, yes? Are you holding, guys? Do you understand, or it's now getting more and more too much? I see some people disappeared. They don't want me
So
to.
can you scroll back up a little bit?
Yes.
My notes, thank you.
The image and the logic, guys, should make it very clear. Look at this picture. This makes it intuitively clear. You see, because the angle is fixed in the first quadrant, I mean, be careful in assuming that this is a complete proof. It's a sort of crutch for the proof. The proof is logical. Good? You understand? I mean, I just used this part really. Sine of an angle is cosine of pi over 2 minus that angle. That's really how you prove it. This geometric image illustrates those identities. You see, it makes you believe that those identities must be true. But be careful, a picture, just, I mean, in here I drew it in the first quadrant, you understand? What makes it so reliable is that I drew it in the first quadrant. Whereas my proof, if you look at the logic there, it does not really depend on the picture at all. Right? I proved cosine of a difference of angles. You think about why that proof is right. It does not depend on what is alpha and what's beta. So now I can figure out, using that idea, I can figure out what is sine of beta plus alpha, because sine of beta plus alpha is the same as cosine of pi over 2 minus beta plus alpha. I can always take the angle, replace it by pi over 2 minus the angle, and replace sine by cosine. And then I can regroup, and I can say this is the same as cosine of pi over 2 minus beta minus alpha. It's now cosine of a difference of two angles. Applying the formula for cosine of difference of two angles, I get cosine of pi over 2 minus beta, cosine alpha, sine of pi over 2 minus beta, sine alpha. What do I get? This becomes sine beta, cosine alpha. So sine of beta plus alpha is sine beta, cosine alpha. Plus, this would be cosine beta, sorry for the ugly writing here. This is just cosine of beta, sine alpha. I obtain this formula. You see that? And then here I have sine of beta minus alpha. I just simply write it as sine beta plus minus alpha. I can apply, now that I have established this formula, beta minus alpha can be written as beta plus another angle. And what do I get? I get sine beta, cosine minus alpha, plus cosine beta, sine minus alpha. And I just then interpret, this is just simply cosine, this is minus sine, and I get this formula. So here are the four formulas which I do hope you decide to understand, you know, that you can derive them. And it helps, guys. If you make shortcuts, you don't understand the material, you are not experienced. You will easily make mistakes because you have no idea what anything means. Okay, so this shortcut is it's actually, knowing is actually a very good shortcut. If you understand, it's the best shortcut. How are you holding, guys? Are you exhausted? You look exhausted. I mean, I look at the few faces I can see, and those faces, I wonder, do they understand me, or do they just hear theta, sine, minus, plus, distribute, sine alpha, sine beta, you know, right? Beta alpha, alpha beta. Is that what you're hearing, or is it comprehensible what's happening? Honestly, I mean, it's okay. Exactly, right? All right, so maybe it will be fun for you to listen to this in case you are not aware of it, right? So I hope that you understand that it's not so much, that we need to figure out what's root of 5 or what is sine and cosine. It has been understood before us, right? It's already evaluated and efficient, and machines do that. But what you try to understand, and that's very difficult and perhaps meaningless when I mention that, because what you try, if the subject is something useful to you guys, it means that it enhances you philosophically, and it enhances your ability to think. Right? So in other words, hopefully sharpens your ability to think. And here is an interesting, simple example about how, you know, ordinary people think, and how people that are mathematically and logically trained think. And of course, it would not be a new example if you have seen it before. I just find it a very easy, and it's very, very famous. Okay, so you know, during World War II, there was this statistician that examined aircraft. They needed his expertise to suggest where should this aircraft, this bomber, have armor added to it. Okay, which parts of the airplane must be armed. And I'm sure that many of you know that. If you know it, keep quiet, guys. If not, listen carefully, right? So to be simple, let me divide it into 3 parts, okay? This is part 1, this is part 2, and this is part 3, yes? And let's say that the airplane that came after their bombing campaigns, the bombing missions, they had this, right? So this airplane, you see the front part is riddled with bullets, the back part is riddled with a few bullets, and the midsection, let's say, is completely nice. It's not riddled with bullets. Where do you add? Oh, Elazar, you tell me what happens when you waste your time on philosophy. You should send it to me to email. I would lose this very remarkable link, which I would very much like to see. Maybe I'll open it after we are done with the class as well. So where should I add up armor, guys? In sector 1, sector 2, or sector 3? What do you think? So Safa says add it in sector 1. Okay, Safa, thank you so much, right? So let's see how many of you say sector 1. So 1, I see quickly. Well, you can put it on my epitaph, honestly. That's exactly what I think. A poet, philosopher, and a complete failure, right? A donkey trainer. So Safa says 1. Again, guys? Okay, we have 1 person for 2. Did you just process it, Aaron? Right? So I'm sorry I called you donkeys. Now I will call you slow donkeys. 2, 2, 2, 4 2s. 2, I think. So a lot of you are saying 2. Well, wonderful. You are actually pretty good, guys, right? So a lot of you are saying 2. And to avoid wasting your time further, why is the answer 2? Because look at it. This means that damage can be taken in the front sector and the airplane will land. I mean, I'm not really using the actual airplane. It doesn't matter, right? The idea is, right? But the planes where the midsection was damaged, they do not come back. You understand? So if it was not natural to you, if it was natural, then you're on the right path, guys, right? In mathematics, the things that are counterintuitive are very interesting. That's, for instance, why I'm drawn to it. I have an affinity to things that are very, very upside down, counterintuitive, and twist everything, right? Equivocate, twist everything, whatnot. Yes, precisely. Those are known as paradoxes, and I like the ones in philosophy, and then I realized the ones that are interesting are coming from mathematics, and that drew me to mathematics. Good. And I hope, I mean, you can enjoy similar things. If you're susceptible to that, then you're very susceptible to what is interesting to me. If not, I do not know. So that's the answer. You understand? That's just a very, very simple example of this idea. All right, guys, we have another 15 minutes, right? Can you hold? Are you still holding? You're okay? Spring is beckoning you to go outside, right? The birds are singing. And you are spending time with me. Well, it depends where, right? In some places it's 7:30, in other places it's morning. Well, somebody already escaped. I just, as I was mentioning, I inspired somebody to leave this lecture. I see it was 28 and now it's 27. Oh, here you go. Abhishek says it's 5 a.m. So for Abhishek, birds are singing, right? There is, by the way, a German expression. It's called he has birds in his head, which means he's crazy. Yeah, so that's an expression. So for people that whose birds, yes. Yes, well, we all are kind of strange, right? I had one guy. He taught mathematics, right? And he's a very strange person. He never ages, right? He looks through all the years. He looks like he was 12 for 29 years at least, right? And he's very smart, but I mean, I tell him probably his mother dropped him on the ground infinitely many times. That's how he came to be what he is. He actually teaches at Brooklyn College now. It follows this place. Maybe you'll have a chance to see him. Well, you're close. His name is not who and it's not he, but you're getting closer. I cannot tell you. Who knows? Me? Oh, hello, Jasprit, and the person right over there. Well, maybe I see double. Who knows? All right. Are we ready? So now we talk about, I hope guys I try my best to entertain you right now. Let's go back to the real entertainment. So what is cosine of 2 theta? Cosine of 2 theta is the same as cosine of theta plus theta. Ah, you know Jeff Suzuki. No, Jeff Suzuki is there's yet another interesting story. Guys, the very first book that I've ever gotten, long time ago in mathematics, was History of Mathematics by Professor Suzuki. And he was not anywhere in New York, as far as I know. And later on, he came to Brooklyn College, and I would just recognize him. It must be, I thought, I hear the name Jeff Suzuki. He came to evaluate how well I teach the class. And then I wanted to bring my book. I thought it must be him. I wanted to bring my book to get his autography. So I get it signed from him. Well, you know Jeff Suzuki. Oh, interesting. Well, I always teach at Hunter. I never left Hunter. Right? Maybe I'm at Hunter now. So cosine of 2 theta is cosine of theta plus theta, which is what? Which is cosine of theta times cosine theta minus sine theta sine theta. Yes? So that was cosine squared minus sine squared, which is what? Which I can convert cosine squared minus sine squared. I can convert to what? I can convert it to 1 minus 2 sine squared theta. You agree? You understand how I convert it to just having sine? I just take cosine and write it as 1 minus cosine squared. So I write cosine squared as 1 minus sine squared, and that gives me this formula. Do you all see that? Or I can decide to convert sines into cosine. Sine squared can be written as 1 minus cosine squared. And if I do that, I get this formula. Also, I have sine of 2 theta. It's equal to 2 sine theta cosine theta. That's a very interesting idea. Yes? Let me show you one small thing. one of the hardest things that I programmed as an animation was this thing, guys. Okay, look at it. I was tremendously proud of it. I'll explain to you in a moment. I wonder, before I explain what it is, if you can tell me what is this thing. Any ideas? What is this? No? Like a what when where question. What is this thing? Well, obviously, but what is this? What is this particular thing? Okay, a cloud. All right, let me show you another animation of this, if you don't see it. I'll turn the sound, I don't like it. So I had a while ago a student, it's a sort of very good student in Calc 3 from the first semester when I started teaching there at Hunter. And he was, also interested in engineering, and he showed me some sort of, he asked me about the square wheel problem. He mentioned that he has this, we've seen in this museum of Mathematics or some other museum, this thing, the square wheel, right? So that's what this is showing, right? You see, here is a bicycle, and if it's a circle, the wheel on a flat ground, it allows you to roll very nicely, where the axle of the bicycle is not bumpy, right? It's just moving. If you look at the axle of the bicycle, it would be moving in a horizontal line. Yes. But you cannot do that with a square wheel. You see, if you have wheels made of squares, that's not going to work. And the question is, what must be the ground to allow a square wheel to roll smoothly? You understand? What must be the ground? Yes, so what must be the road for which the square wheel will be riding smoothly? You understand? So that the axle of the wheel does not change. Yeah, it must be a bumpy is good, but precisely what it must be. Engineer a road that will work, right? And here it is, guys, you see? This is the shape of the road by which it works. So I wanted to understand it, and of course, well, I just did. Yeah, you cannot write fast. That's another thing, right? So here is the thing. So I then I wrote the equations. I wrote all the motions. You see, guys, when you say a square rotating, I'm translating. I'm describing a square using trigonometry. You understand? I'm using all those ideas to be able to just even try, guys. Think about it. Can you describe a square? Just to describe the shape of a square using trigonometry. Can you do that? Just trigonometry, right? I mean, the circles easily, right? The point on a circle is cosine, sine. How do you describe a square using trigonometry? And then rotate it and all that nonsense, right? And then figure out, I used a lot of calculus to figure out what sort of shape of road it must be. And then I put it all together in that video to prove that my mathematics works, the one I described. Then I was very proud of myself, right? I'm so smart, And then I showed it to my brother and said, what a moron you are, right? Just take a square wheel, take Play-Doh and roll it into it, and that will press the shape into the Play-Doh, and that will create the right road, right? Without doing any math whatsoever. I just press it into the Play-Doh and it will create the shape. You understand, guys, what I mean? And this is the challenge of the subject. The challenge of what I'm trying to tell you is what you have is a sort of battle without rules, but in this battle, you're trying to be smart or trying to, right? So it's just Right? So that's what I'm hoping you get from this class. It's not root, it's not this, it's not that. Is that you are in a warfare without rules, where you're trying to be as smart as you possibly can. And what my brother suggested, you see, I always think about it, right? What's the mathematics there? I described it, that's wonderful, but take Play-Doh, take that and roll the square wheel and it will create the road. You don't have the description of it, but you have the road. Yes, now of course I have only one brother, the infinity brother, precisely, right? Pragmatism versus philosophy, right? To me, I just describe things passively. I don't want to build anything, right? I do not even think that I use those things for anything. I just kind of use this. I just contemplate, right? But I'm hoping, so that's the only thing I can help you train, guys. You can maybe contemplate and touch things, but up to you. I'm just contemplating. My eyesight is the only thing that I have. What? Poet, philosopher. Okay, poet, philosopher, failure. Let's search for those words. Do I search image? Yes. Well, it combines my love of cemeteries, Elazar. You know, one of my favorite places to go to is a cemetery, and I know many poems about cemeteries, naturally. Right? Good. Yeah. Do you want to go through half angle formulas, or you had enough for today? What Erin means no, you did not have enough, I understand, right? You want more. Yes. No more, please. All right, so I will stop the recording. And if you're interested, a round of what, when, where, or if you have questions, we can address those questions. Or what do you like to do, guys? You like a beautiful song? You want to listen the song about trigonometry, the radius, or something else? The radius song, okay. Abhishek wants what, when, where. Abhishek is correct. That's the best thing that we do. But we'll listen quickly to a song on the radius before you go.